Okay, so now that we know the 12 basic functions and we know the properties of functions, we're going to build functions from functions. So we did this a little bit last year. We did. The only thing new is really the domain idea. We added, subtracted, multiplied, divided functions. Composing functions is f of g of x, g of f of x. The new thing is being able to find the domain of these functions. That's the part that really is new. Um, you're combining them algebraically. Um, why are we looking at these? Really, I mean, that's the biggest thing here. Most of the functions that you encounter in calculus in real life can be created by combining or modifying other functions. So it's like I put a line with a parabola, you know, y equals mx plus b and an x squared with an absolute value. So if f and g are two functions, algebraic combinations defined below. And the thing that you want to remember with this is you can see it either way. So I could ask you to do f plus g of x. Well, what does that mean? You take f of x, you take g of x, you add them. You can see either way. The thing with sum and difference, what do we want to think? We are going to combine like terms. If you can't combine them, then you just put a plus sign between them. Multiply, this is f times g. That's not f of g. So they're right next to each other, or it says fg of x. With that, distribute if you can. If you can't, you know, if you have a x times an absolute value, you can't distribute that x into absolute value, so you just put a times sign between them. Quotient, f divided by g. This was when we first started. There were exceptions. You have to remember that g of x cannot equal 0. So that's really where this idea of the domain, the new domain, has to belong to both the domain of f and the domain of g. So what will end up happening is you're going to find the domain of f, you're going to find the domain of g, you're going to find your new function, and then you're going to make sure that the domain of the new function has everything in it that was in it before. Sort of have to see it. So f of x is x squared, g of x is the square root of x plus 1. So I always tell people this idea of domain. Find the domain of the original first. So f of x, x squared, is a polynomial. Its domain is negative infinity to infinity. G of x is a square root. Well, I know with domain, a radical has to be greater than or equal to 0, which would mean x would have to be greater than or equal to negative 1, which means its domain is negative 1 to infinity. So if you really think when you're putting these things together, the domain of the new function had to be the domain of both of those combined. The g of x domain is the one that really matters, because the fact that everything works in f, everything does not work in g. So the most that the new domain can be is negative 1 to infinity. So f plus g. f plus g would mean I'm going to take x squared plus the square root of x plus 1. There is nothing I can do. I'm done. Now, the domain of that, what can it be? Well, this thing right here has to be negative 1 to infinity. So the domain of the whole thing is negative 1 to infinity. F minus g, x squared minus the square root of x plus 1. Same thing. Nothing I can combine. I leave it. F times g, x squared times the square root of x plus 1. I can't distribute an x squared into a square root. I'm done. Domain, same thing. The most it can be is really the intersection of those two domains, which is negative 1 to infinity. F divided by g. Well, f divided by g, if I put f over g, well, I can't do anything. But now I have to think about the domain. The most the domain can be is negative 1 to infinity with a bracket. But now that radical is in the denominator, which means it also cannot equal 0. So now my domain changes to negative 1 to infinity. And then the last one was g times g, which actually is a good one to see. G times g means really you're taking the square root of x plus 1 times the square root of x plus 1. And if you square a square root, that means you're going to get x plus 1. Now, this is where this domain idea really comes up. You guys look at this by itself. You would tell me that the domain is negative infinity to infinity. But it can't be because of the original function. The most it was negative 1 to infinity. Graphing calculator really shows this. You know, if x plus 1 is a line, if you put in the square root of x plus 1 times the square root of x plus 1, in your graph, you can see that that domain is negative 1 to infinity. That is a line that has a y-intercept of 1 and a slope of 1, but it does not go below negative 1. And if you looked at the table, you can see that all those things less than negative 1 give you error. And it's because of the original function. Okay, so that's really where the domain comes in. And so I really just did that. So composition, f of g of x, f of g of x, g of f of x. Remember, we looked at both of these. This is of. It's not a closed little dot. It's an open dot. So don't think that that's times. F of g of x means I'm putting g into f. G of f of x means I'm putting f into g. Domains. So the domain of f of g consists of all x values in the domain of g that map to values in the domain of f. Now really, what does that, like my little star, mean? Start with the domain of the inside function. That's the most it can be. But it might be less than that. So there might be further restrictions required by the new function that you have to be careful with. Okay? So we're going to just do these two, f of g, g of f. Again, I like to think of my domains to start. F is negative infinity to infinity. It's a polynomial. G, radical, greater than or equal to 0, 0 to infinity. So if I ask you to do f of g of x, I'm putting g in to f. So remember, I do prefer that. I'm putting g into f. So I'm going to take this whole thing and I'm putting it in for that x. So I would have the square root of x squared minus 1. Well, what happens is when I do the square root of x squared, I get x minus 1. That's f of g of x. But now, what's the domain? If you look at this, you're going to tell me negative infinity to infinity. The most the domain can be is the domain of g. So what was the domain of g? 0 to infinity. And nothing else won't work in that function. Again, a graphing calculator really can show it. If you take the square root of x and you close that and you square it, minus 1, you get a line whose x starts at 0. You can see 0 is the first x that worked. So now if I did g of f of x, with g of f of x, the domain could be negative infinity to infinity because that's f's. So I'm going to plug all of this in for that x. So I'm actually going to have the square root of x squared minus 1. And there's nothing I can, don't distribute your radical, that is it. Now the thing is, people will say, oh, domain is negative infinity to infinity because that's what f was. You now have further restrictions because you have a radical. That radical has to be greater than or equal to 0, which means x squared has to be greater than or equal to 1, which x has to be greater than or equal to plus or minus 1. And remember, this is that 1 gives you the same thing as negative 1. 2 gives you the same thing as negative 2. So with this, it's that stuff and that stuff. That's not negative infinity to infinity. That's negative infinity to negative 1, 1 to infinity. So that's everything, but the stuff between negative 1 and 1 won't work. So you really have to be careful with that. Last thing, decomposing functions. A lot of this is used in calculus. Decomposing functions allows you to think of a complex function in terms of two simpler functions. So in the composition, view f as the outside, g as the inside. So you're trying to think, I need a g that I plugged into f to get the answer. So I give you h of x. And I say to you, you give me a g and an f that gave you that answer. So if I looked at this first one, h of x is the square root of x squared plus 5. How could you have gotten that function? You plugged g into f and you got that. So the answers vary. Some people, after you see a couple, you'll see it. I could have said G was x squared plus 5, and F was the square root of x. If I would have plugged G into F, that would have given me that function. Some people look at it differently, and they could have had, it's hard for me, I see it one way and it's hard for me to see it a different way. F could have been the square root of x plus 5, and G could have been x squared. If you would have plugged x squared into the square root of x plus 5, you would have gotten h of x. If I look at another one, h of x is 2x plus 1 cubed. If I say g of x is 2x plus 1, and I say f of x is x cubed, if I plug g into f, I would get that answer. Likewise, you could have said g was 2x, f of x could have been x plus 1 cubed. If you plug g in for the x in f, you would have ended up with that answer. This last one, if I said g was x minus 2 and f was 4x to the 7th minus 5, that would have given me, if I plug g into f, that answer. So those are some possibilities. You could think of others, but the answers do vary. That is really used more in calculus, but it is an idea of composition. So hopefully that lesson, just be very careful with the domain and make sure you find the domains. If you're not finding the domains, you're not really working on new stuff. That's the hard part. Okay, we'll see you next class.